All right, welcome everyone. This is the final chapter of the Mathematics for Machine Learning book. Um, Unfortunately, Anastasia volunteered to lead today's discussion, but she's been sick all week, and so she's not able to um, be our presenter for today. So I have her slides, and I'm going to be covering here. So we did part one, which was all of this theory, and now we've got a handful of chapters on different use cases. And so today we're going to talk about classification and we're going to talk about support vector machines. So here's a brief agenda, um, what Anastasia outlined. So a quick refresher on inner products. We're going to talk about what they call the hard margin SVM problem, go a little bit deeper into the margin and the formulation of the problem, a refresher on Lagrange multipliers, which were covered back in the optimization chapter, whatever that was, 7, 9, something like that. That has to do with constrained optimization. And so then we'll go and we'll look at this SVM problem, and we'll look at the dual using Lagrange multipliers. And then finally, we'll talk about the kernel trick. So this chapter is a little bit weird. We're going to have a lot of time we spend on the formulation of the problem, and then we're not going to talk about how we actually solve the problem, how we actually get the answer, optimize our parameters. And we're going to go through several different formulation steps, gradually getting more complex and looking at different perspectives. And only at the end are we going to sort of actually try tackling the problem. And then ultimately, we're not even going to really do it. It's just going to say, so from here, you can see that you could like write the code and you could do the various steps to solve this, but we're not going to actually go through. So the focus on this is really about how we can take all the math principles we know, take a geometric interpretation, and then we can formulate classification. The other thing that's super interesting is that the SVM is a linear model, and typically in a linear model, you're fairly limited in how much representation, how sophisticated your representations can be. So they talk about this concept of you can always like modify your parameters. So previously we talked about if you had an x, you could also have an x squared, and so you could turn linear regression into polynomial regression. You can do a similar thing here, but unfortunately, what happens is that the calculations grow combinatorially, and they get very expensive very fast. So, for example, if you have 100 features and you want all the pairwise quadratic combinations of those two, there's 10,000 or half that, whatever, 5,000 pairs of these. And if you go to like third order, it just keeps growing combinatorially like that. So it'll turn out that the most important thing that makes SVMs more useful than they otherwise would be is when we get to the very end and we talk about kernels and the kernel trick. That allows us, in some cases, to have a kernel where the calculation is much less expensive than if you just did it the brute force way. So that's a little bit of a preview in terms of like why are we doing all this. Part of this is just to understand um, this use case for a lot of the math we talked about, but then ultimately this kernel trick ends up making SVMs fairly useful. I think these days, gradient boosting, I would say, is still probably the default go-to for tabular data. And then for more complex systems, deep learning has sort of replaced SVMs. But it's still a very good technology to understand, and it helps us solidify our understanding of the math that we've been talking about in this book. So it's a good capstone for this book. All right. So first a refresher, and then just a comment for people online. If you raise your hand, that's the easiest way for me on one screen to see you have a question. You can try unmuting, but I'll need to make sure that all of the AV is set up properly for that. So the first time somebody raises their hand, I'll make sure the audio is set up properly. Okay. So if we use the Euclidean dot product, the inner product, then we have some geometric intuition here, and we can say that basically this is the arc cosine, and so basically the dot product will tell us a lot about or rather, the dot product itself is the cosine of the angle. Okay, if you want to get the angle itself, the theta, then you would do an arc cosine. But so if you have two vectors that are pointing in the same direction, then the cosine of 0 is 1. And so this is the maximum possible value for your dot product. If they're 90 degrees apart in Euclidean geometry, they're perpendicular, they're orthogonal, then your dot product's going to be 0. So what this Euclidean dot product tells us is the similarity in direction, where if they're the same direction, it's a maximum value. If they're orthogonal, it's a minimum value, and you get a continuous value in between. There are other inner products that are not the Euclidean dot product, okay, but they still can be interpreted as a similarity metric that has a maximum value when the vectors are identical and a minimum value at some definition of orthogonal, which is not the Euclidean definition, okay? But the important thing to know is that any inner product can be used as a similarity metric. We're going to go through all of the discussion until the very end, just thinking geometrically in terms of Euclidean space, using all of our intuition around the geometry of objects. But just want to mention that inner products don't require the Euclidean relationships. All right, so what is this problem we're going to set up? We've talked about regression, okay, where we have a continuous output. So now we're going to talk about binary classification. And you can see the picture on the left that you imagine that you've got a bunch of samples, a bunch of data points, and they fall in one of two classes. So the orange X's are one class, the blue circles are another class. And for convenience later on, that you will see why, we're going to denote the classes as -1 and +1. It'll turn out to be very convenient when we multiply by either +1 or -1 later on, okay? You probably have seen other places where they've been represented differently, 0, 1, or however, but conceptually, it's not super important. You just have two different classes. And it's easy to show for illustrative purposes data that's two-dimensional, because we all have pretty good intuition around the plane. And so here on the left, we have two-dimensional data, and it's pretty easy to imagine drawing a line that goes through this. If we had three-dimensional data, you can't separate the data with a line. You would need actually a plane in order to separate them. And in general, if you have d-dimensional data, you need data that's one smaller. You need d-1 dimensional data in order to separate them. So there is a mathematical term for that most people have probably heard before, which is hyperplane. And so the SVM, like a lot of other ML literature you're going to read, talks about the use of hyperplanes. So our job is to take the data and fit a hyperplane that's going to do a good job of separating the two classes from each other. In order to figure out what we mean by good job, we're going to introduce some other concepts. So let's talk a little bit more about what how we would mathematically represent a hyperplane. So in section 12.1, there's some material here, and the key idea is that if you were to write, I'm thinking about like algebra that I took in high school, algebra 1, algebra 2. If you were to write on the R2 plane the equation for a line, you might have learned, there's multiple formulas for it, but one of the formulas you might have learned equals y equals mx plus b, okay? So you need two quantities to define that line. You need the slope m, and you need the y-intercept b, okay? Turns out that in general, with two objects, you can define a hyperplane in any number of dimensions. The one thing that changes, though, is that when you say y equals mx plus b, m and b are both scalars. They're just real numbers, okay? We're now going to say y equals wx plus b, and w is going to be a full-length vector. And when we say wx, what we're going to do is we're going to take the inner product of the two, okay? So the inner product returns just a single number. It's no longer a vector quantity. And b will stay a scalar, a single number. And so Wx plus b could be 0, could be 1, could be -5, could be 3.2. Okay. If you have the equation y equals, or if you have the equation Wx plus b equals 0, that will define a hyperplane. Okay. In any number of dimensions, it will define a hyperplane. And if you do a little bit of noodling, then what you will see is that the hyperplane that's defined by the equation Wx plus b equals 0 is always going to be orthogonal to the vector W. All right. And if you just had b equals 0, so if you just say Wx equals 0, it's going to be a hyperplane that goes through the origin. If you say Wx plus b equals 0 and b is not 0, then actually it's going to be offset in the direction of W by an amount b. Okay, so in just 2 dimensions, you can see that our hyperplane is going to be a line, okay, and that this line is orthogonal or perpendicular in terms of Euclidean geometry, perpendicular to our vector W. So here's the origin, here's our vector W. The equation, Wx plus b equals 0 is true for all these points x that are along this perpendicular line. And this is generally true. So in 3D, you could basically say, here's this W vector, and you have this plane that's orthogonal, that's perpendicular to this. And in D dimensions, it's just this D minus 1 dimensional hyperplane that's orthogonal to our vector. So a single vector, a single direction is enough to define a hyperplane, and then you just need this B as an offset because there are multiple parallel, so to speak, hyperplanes. All right, so there's a bunch of different math here, and when we talk about our classification problem, what we're saying is we want all of the, we're going to now name them positive data points to be on the positive side of the hyperplane, which means that Wx plus b, instead of equaling 0, that's the definition of the plane, we want it to be greater than 0 for all the positive examples. We also want it to be less than 0 for all the negative examples, and because we use this convenient +1 -1 naming convention, we can now have this single equation where we just multiply our expression Wx plus b by the label that's +1 or -1. And so the -1 basically turns the greater than into a less than effectively. And so this is just showing us how we can take our formulation, our idea of points in D dimensions living on either side of the hyperplane, and we can express it mathematically by saying label times our hyperplane equation Wx plus b is greater than or equal to 0. So this is now just our formulation of classification. Any questions? Comments? All right, keep going. So now we're going to talk about the margin, and the intuition behind this is if you see these points here, the blue and the orange ones, there's multiple hyperplanes. In this case, it's just a line. There's multiple green lines that you could use that will separate the green from the orange. I guess if I look at this one, yeah, I guess this one still, they all successfully divide all the orange on one side and the blue on the other side. Intuitively, you might feel like some of these feel better than others. Like this one over here comes super close to these blue points over here, and this one over here comes super close to this orange point over here, to the point where it even crosses the drawing of the X, but I guess technically not the center of the X. That confused me at first. And so it seems like those two lines come unnecessarily close, to any of the points. And so there's a lot of formalism for something that I find geometrically fairly intuitive, that you might say the safest line you can draw is the one that stays as far away from the orange and the blue points as possible. Because we've labeled whatever this is 25 blue points, but maybe there's another blue point close to this one that's just right over here. So why would you get so unnecessarily close if you could just stay farther away? Okay, or maybe there was a little bit of error in measurement error in this blue point, and it actually should be a little over there. So really, we're going to have some formalism, but we're basically just saying we're going to need a very formal definition of close and far, and we're going to have to set it up mathematically so that we can formally do an optimization to say what is the equation of the line or the hyperplane in general that is the farthest away from all the points. That's really where we're trying to go to. So that's the geometric intuition. So there's a bunch of formalism here. And the idea is if you define your hyperplane as wx plus b, okay, here's our vector w, and then here's our hyperplane. Any point that you have, we're gonna call this one x sub a. A doesn't stand for anything particular. It's just a random data point. Basically, if you take the projection of x sub a onto our hyperplane, you're going to be moving it via this dotted line onto the point x prime. Okay, and we can then measure the distance between xa and x prime along this dotted line, and we'll call that distance r. Okay, and we can do this for every point, and we can basically see how far are all the points from our separating hyperplane. There's a bunch of math here, and basically in the original formulation in this book, they say the simplest way to understand this is imagine that you require that your direction W is of unit length. So if you do that, then that properly sort of scales things. And so W divided by the W norm will just be W if it's length 1. And if it's not length 1, then we'll have fixed W to become length 1. Okay. And so if you do the sort of vector math, you can see that the original point X equals the projection point X prime plus R times unit W. And so again, we've now defined a way to say how far is any given sample from the hyperplane, and that will be the number R. R is our margin. Okay, some will be closer, some will be farther. I don't know if for me this seemed like a whole lot of math for something that seemed fairly intuitive to me, that like some points are closer and some points are farther. But basically, what they're just saying is you're going to take the shortest distance between each point and the hyperplane, which is always going to be the orthogonal direction, and it's going to be the difference between the projection and the regular point. I think there's another slide here. Yeah. So if we define a good hyperplane using our wx plus b equation, then what we want is to have r, which is the smallest distance between any point in the hyperplane. We want to maximize what that r is. Okay. And so the formal definition is we want the maximum value of r given that we have this equation where all the points are r distance away or farther. And we assume that our W vector is unit length. And then R is positive numbers. We're just saying we're going to represent it that way. You could use negative, but it's just much more intuitive to use positive numbers. So this is a formal way of saying how far is the nearest point from our separating hyperplane. This is not, however, how the original papers and most textbooks talk about the SVM. So I believe the next slide, they say there's this traditional derivation which doesn't assume that the length of W is 1. I didn't find this section to be terribly important, but I guess it's useful because if you're going to look at SVM written somewhere else, you should probably understand that their notation is going to be different. And so what they talk about is scale your data until you get the margin R equals 1. And so for me, it was pretty intuitive. Like, well, if you just take our formulation and you divide everything by R, then what used to be R becomes 1, and then what was W becomes W divided by R. And it seems pretty intuitive to me, but they go through long lengths with a lot of math to basically show, like, hey, we can prove all these things, and eventually you get this equation down here. And then we know that Wx plus b is the equation of a hyperplane, so that's 0, so that's going to go away. And the inner product of w with itself is going to be the norm w squared. So then we can further simplify. We get this equation. We can move things around. And we get r equals 1 over the norm of w. And like this is just like a whole lot of stuff to basically divide both sides of the old equation by r. But nevertheless, so they say what you're going to see in other books is maximize 1 over the norm of w subject to this equation that the points need to all be 1 or further away from the margin. And because maximizing 1 divided by something is kind of a pain in the neck, what they do is they flip it, and these are all positive numbers, okay? So it's different if they're negative. So what they do is they just flip it and they turn it from a max to a min, okay? So this becomes a min of w, instead the norm of w, instead of the min of the reciprocal. But if you're minimizing w, you're also minimizing w squared for positive numbers. And if you're minimizing w squared, you're also minimizing 1/2 w squared. So you're going to have the exact same values of your parameters, whether you minimize w squared, or 1/2 w squared. And it just turns out that 1/2 w squared is going to be very convenient in later equations. So we're going to choose this as our objective for what we minimize. And so this is now the formal definition of the support vector machine that you're going to see in most other books, apparently. Okay, so we're going to minimize this 1/2 norm squared, subject to all the points are at least 1 away from our margin. So we went through a bunch of math, but the intuition is still the same. We just want to divide all the points, and we want the hyperplane to be as far away as possible. In this case, we just scale the data until the points are exactly 1 away. Questions, comments? Yeah.
What is the
So the Euclidean thing would be you take the dot. Oh, can you get the door? You take the dot product of it with itself, which basically means you just get first term squared, second term plus second term squared plus third term squared, and then you take the square root of that whole thing. So square root, always square root, yes. So it's an L2 norm. So in in R2, you get the Pythagorean theorem, where it's just square root of a squared plus b squared. That's your C, okay? But yeah, in R5, it would just be x1 squared, x2 squared, 3, 4, 5 squared, and it's still only square root. It's not a fifth root. It's always square root. So you can think of that as the length, if you just want a very not math rigorous but simple term for it. In this case, we're really talking about like the inner product of w with itself is the norm of w squared. Cool. Any other questions? All right. So now we've defined this problem, and we can just go and we can solve all of our classification problems with this support vector, right? But we kind of have a problem. This assumes that all the data is linearly separable. And in the real world, most of the time, the data is not linearly separable. So we're going to need to complicate our SVM before we can actually use it very much in the real world. So now we're going to have this idea of a soft margin. And I think the geometric intuition is a lot easier to understand than some of the heavy math formalism. But so imagine that we've got here our W vector, and we've defined this hyperplane, which is the solid line in the middle, Wx plus b equals 0. We've now got our margin defined where we've got one above it is WX plus B equals 1, and one below it, not labeled, is the second dotted line, WX plus B equals minus 1. And all the positive points are supposed to be up here above on or above the WX plus B equals 1 dashed line. This is like, I don't know, I think algebra 2 is where you start doing like, instead of just equalities, you do inequalities, right? So instead of saying like mx plus b equals, 0, you say like mx plus b is greater than 0. And so then you have to shade one side of the line, right? Same thing here, right? So all our points are supposed to be on this side. But what do we do if we have a positive point that instead of being on this side of the line is a little bit on the wrong side, a lot on the wrong side, or even so far on the wrong side that it's beyond the margin for where the negative points are supposed to be? Well, all these cases fundamentally just mean it's on the wrong side. And so we're just going to measure how far is it on the wrong side. So the same way before we measured R to say how far are you on the right side, right? We're just going to say this variable. And so this is the Greek letter. I don't know, different people pronounce it different ways. Xi, Xi, whatever. I'm used to calling it Xi, whatever, right? So it's the one that comes after nu in the alphabet. Okay. So we're going to use this Greek letter Xi to represent how far you are on the wrong side of the line. And there's the similar effect if you have negative points that are on the wrong side of the other margin. Okay. So a simple way to think about it is we're going to penalize for having points on the wrong side. So whereas before, where's my mouse? We minimized 1/2 of the norm squared. Now we're going to minimize the 1/2 of the norm squared plus our penalty, which is the sum of all of the Xi values for points that are on the wrong side. So if all the points are on the correct side, they're all these X's are 0. And so this whole thing goes away, and it's just our original hard margin problem. But to the extent that we have 1, 2, a handful, some number of points that are on the wrong side, these will be non-zero, and we'll have an extra penalty here. So you can imagine in the hard margin case, where all the points were linearly separable, it's possible to have all of these be 0. So you're probably better off just picking one that does successfully divide them rather than having non-zero values here for the thing that you're minimizing. The positives are on the wrong side and the negatives that are on the wrong side for them. Psi or Xi is always a positive number representing how much a point, positive or negative, is on the wrong side of its margin. So it geometrically means something different for positive class and negative class, but it's always a positive number measuring the distance that it's the wrong side of, the kid that came from the wrong side of the railroad tracks, that kind of a thing, right? All right, now we also throw in this magic constant, capital C, which tells us how much do we care about penalizing you for having points on the wrong side. Okay, and so this is a good point to pause. The book mentions it here or a little bit later, but ultimately, when you minimize this based on your value of C, you get to decide how much do you care about having points on the wrong side versus how much do you care about having a really wide margin. Now, in a perfect world, you can have both, okay? But in the real life, it tends to be not that awesome. So imagine, I don't have a good example, but if we go back to our points here, okay? Imagine that it looks just like this, except I have one extra blue dot, like right over here, right near the orange X's, okay? If my penalty for having a point on the wrong side is really tiny, 0.01, then for the most part, I just pick the same green line I was going to before because all I'm doing is trying to maximize the margin and I'm ignoring that 1 point that's on the wrong side. But if my penalty for having a point on the wrong side was 1 billion, then what that would do is that would cause my green line to shift all the way to be right here, right next to all the orange X's, just so that I could get that blue dot on the correct side of the line. Okay. So when you have this constant big, small, one value is going to say, an extremely large or small value is going to say, I just care about having the margin. It doesn't matter if a few points are on the other side, whatever. As long as it's a small number of points, just ignore it. And then the other value for your constant is going to say, no, 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 don't have points on the wrong side. That's a really, really big deal. I would so if you had that and you had a blue dot, like, I don't know, whatever, but it would have to basically like shift the line so much to minimize the number of points that are on the wrong side. So let's say you had, like, I don't know, not just one, but you had like 10 blue dots that are way over here, 10 orange dots that are way over there. It's going to like contort the line in any direction to say, can I get only 9 points to be on the wrong side? Can I only get 8 points to be on the wrong side? And it's not going to care that the margin is completely nonsensical at this point. Again, that's assuming like infinitely large or infinitely small values of C. So I hope that geometric intuition makes sense.
I have a question.
Oh, please.
So, but now the premise is to pretty much take all the points.
Yep.
And we look for like the smallest distances. How is this different to linear regression? It's like if we look at like W times X in a product, it's just like linear regression, right?
Yeah. So this is a linear model. And so essentially you can think of this as being like linear regression, except the difference in linear regression is we're predicting a real value and we're seeing, are we close? Okay. So the price of a house, I predict is 600,000. Nope, 700,000. You weren't that close. I predict 600,000. It was 610. Okay. In this case, we're doing classification. And so we're saying there's two classes, cheap houses and expensive houses. And it doesn't matter how close you are as long as you get the class right. So if you said, yeah, I think the house is 600,000, so it's expensive, it doesn't matter if the house is 5 million, you still got it right. And so there's no penalty. So regression in some ways is a don't take this too literally, but in some ways, regression is a more restrictive task, a harder task, because you have to get everything right. Whereas this, it's like, as long as you said it's a cheap house, you might have thought it was 10,000 and it was actually 50,000, but you got the category right, so you just get full credit. Yep. Any other questions? All right. We're now going to take another look at this formulation with some different math formalism, because ultimately we're going to want to program this and we're going to want to solve this. And so this is not necessarily the most convenient thing to solve. So there's a loss function view. I'm not going to read through everything on the slide here, but the idea is if you have this hinge loss function, okay, and so down here in the lower left corner, you can see that our original formulation is sort of this 0-1 thing where it's like there's no penalty if the point is on the correct side of the line. And there is this penalty if it's on the wrong side of the line. That's not differentiable. So what we can do is we can instead pick this orange line, which for the values 1 and 0 have the same values as our 0-1 loss, okay? And so the way we say this is that the hinge loss is defined as the maximum of 0 or 1 minus t. So if you break this down into multiple cases, okay, when t is greater than or equal to 1, then the 0 is the max. When t is between 0 and 1, we get a value that's greater than 0, but based on the value of t. And then when t is less than 0, then we get an even larger value, okay? And so how we define t is this equation here, y times wx plus b. And remember, y is either +1 or -1 because we cheated and knew in advance that it would be really convenient to have a positive and a negative with no magnitude, but just basically changing the sign. All right. Um, so if we use this hinge loss, all right, then we can basically write our equation that we had above this way down here. I'm not going to go through all the steps, okay? But you can see once again, you have this formulation of the maximum of 0 or this other expression, all right? And we can optimize this for the minimum value the same way that we optimize the other one, and we'll get the same answer. Okay, it's just that hinge loss has sort of like other possibilities, but we're not going to worry about that. So, is there another slide? No. Okay. So then, if you're familiar with deep neural networks and our loss functions, it's very common in a paper to see somebody say, hey, we're just going to add an extra penalty term for a loss function, right? We're doing images. We're going to add a reconstruction penalty. We're going to add a perception penalty. We're going to add a whatever L2 penalty. People add penalties like all the time. It's like pretty much every paper. So what we're really saying here is we're going to minimize the margin and we're just going to penalize all the points that are on the wrong side. And this penalty will be 0 for all the points that are on the correct side. And this penalty will be something non-zero, something bad that makes our loss worse for points that are on the wrong side of the margin. So if you want, you can go look at section 12.2.5 if you want to see the full derivation. But basically, if you're not quite following this, you can look. But that's really all we're doing here is saying we're adding a penalty. This one I had to reread like 16 times and think about it. Okay. They do not explain this in the book. Okay. Remember how I was talking about, depending on whether your value of C is really big or really small, you either want to focus on having a really nice margin, okay, or you'll contort that line any which way just to get the minimum number of points on the wrong side in the extreme, okay? Contorting a line to get the points on the right side is kind of overfitting, if you think about it, okay? And having a nice wide margin is probably a good path towards generalization. So anything that helps you towards generalization, we just call it a regularizer. Even if it's not the same kind of regularizer as other things, right? So, we have noise that we add to networks, dropout. We call that a regularizer. Dropout is really not like an L2 penalty at all. It works very, very differently, but it has the same effect of better generalization. So basically what they're saying is anything that's likely to have better generalization, we just call it a regularizer. Okay? And to make things even more confusing, instead of having this magic constant here on the right-hand side, a lot of SVMs have this magic constant on the left-hand side, and they also call it capital C. So you can't say, well, if they call it K, then big regularizes, and if you call it C, no, they both call it C. And so that's why I've been a little bit loose in defining big and small. I just sort of say one and means you really care about wide margin. The other extreme for C, big or small, means you care about getting points on the right side. So this is a hyperparameter that you might do cross-validation or something in order to optimize. There is no predefined C that's like rule of thumb. You should always use, 0.1 as your value of C. A lot of it depends on the scale of your data, right? So if you have data that's about stars and galaxies and everything's on the order of 10 to the 15th power, I imagine your C is going to be very different than if you have something you're measuring that's mostly, between 0 and 1, just because the numbers are so much bigger. Okay, so at this point, like I previewed at the beginning, we haven't said anything about how we're going to solve this, but we have sort of defined, and we now have a definition that is fairly computer friendly. Okay, that we want to minimize this margin plus this little penalty term here. All right, we're now going to go and talk about how would we um, uh, approach this. And if you recall, the constrained optimization that we discussed, I think Ryan was the one that covered the optimization chapter. So there's this Lagrange multiplier technique, because again, what we really want is to say you have an infinite penalty when you're on the wrong side of the constraint and a zero penalty when you're on the right side of the constraint, but that's not differentiable. So instead of doing that, we just have a line that says the further on the wrong side of the constraint you are, the worse the penalty. And that multiplier is going to be our lambda. Okay. That's not perfect. It's not a perfect substitute for the zero infinite penalty. But for many problems, it ends up being good enough, especially if you can achieve zero penalty, then it doesn't matter whether the penalty would have been 1 or the penalty would have been infinity. As long as you stay on the correct side, it's 0. So Anastasia included a little bit of a refresher here on Lagrange multipliers. So we have a constrained optimization problem, and our constraint could be defined as some function g has to equal a value c. Okay, and so imagine that this, I don't know what color this is, blue, gray, is the surface of the function that we're trying to minimize, maximize. This could be our loss function. So if g is defined by this red line, and here we have an equality, we could also have an inequality, okay? Then basically we're trying to minimize or maximize all the points on this blue surface that are on this red line, okay? And I believe one more slide. So we, in our Lagrangian formulation, what we do is we take all of our original variables, and now we start adding in these lambdas. And this lambda is the penalty term. And again, what we really want is to say the penalty is infinity if you mess up, and it's 0 if you don't mess up. But instead, it's just going to be a linear function. It's a linear multiplier lambda. Okay, so the farther away you get from C, this when G of whatever your inputs is equals C, then this expression is 0, and it doesn't matter what your lambda is. And when it's 1 away from C, if lambda is 100, then your penalty is 100. If lambda is 1,000,000, then your penalty is 1,000,000. So this is our Lagrangian. And for convenient small problems like convex quadratic problems, we're going to know that there is only one minimum that we're optimizing for, or maximum. And so the local minimum is going to be the global minimum. And when you know that, then what you can do is you can just set the derivative equal to 0, like you did in calculus, in regular, univariate calculus. And that will define your critical point. That's either, a maximum or a minimum. And so that's what we're going to do. That's the sneak preview. What we're going to do for this support vector problem is we're going to set everything up with our Lagrange multipliers. We're going to take the derivative, in this case, because it's multivariate, partial derivatives of that equation. We're going to set them to 0 to say at that value, we will have a closed form solution for what the minimum is. All right. So here we're going to reformulate our problem slightly. And to keep more consistent with the way other books and papers talk about SVMs instead of our Lagrange multipliers being called lambda 1, lambda 2, lambda 3, which is what we saw in previous chapters, we're going to split them up into two groups, and they're going to be called alpha 1, alpha 2, alpha 3, and gamma 1, gamma 2, gamma 3, and so on. Okay. And the reason we're going to do this is for bookkeeping convenience, and it's going to turn out that the alphas are more important than the gammas, but mostly it's just for bookkeeping convenience. All right. So I'm not going to go through the whole derivation, but we originally had our hyperplane defined by W and B. We have our Cassie slack variables for any points that are on the wrong side. And so now we're also adding our lambdas, but in this case, we're calling them our alphas and our gammas. And so our new equation 12.34 is going to be, again, 1/2 the inner product squared plus C times our slack penalty. Okay. And then here we're going to have this alpha constraint for this has to do with points on the wrong side of the line. And this constraint over here has to do with the sum of all the slack variables. Sorry, I don't remember this derivation exactly. So if we take this equation 1234 and we differentiate it with respect to W, with respect to B, and with respect to all of our C variables, we can set each of those equal to 0. All right. So the first one is we take the partial derivative of this whole equation 1234 with respect to W, and if you do the math, you'll get this expression. Okay. And this expression will equal 0 when W equals this thing on the right. So let me go to the next slide. So you can see by setting that equation to 0, W equals this summation on the right. So what we're going to do is we're going to take this equation 1234, and every place where there's a W in it, we're going to replace it with this summation. And then we're going to expand and simplify. And that will turn equation 1234 into this wonderful equation 1239, which I did not check, but I assume the authors got it right. Okay. And the important thing to note is this blue equation, this blue portion of the equation, these two terms. Okay. You'll notice that these two terms both have a sum over I and a sum over J, and they have YIs, YJs, AI, AJs. They're just in different orders. Okay. And so it says in the book, because of the symmetric nature and the bilinear nature of inner products, you can actually rearrange these terms. And so in fact, aside from the 1/2, these two expressions are identical. So you just basically have 1/2 thingy minus thingy. And so the net result is minus 1/2 thingy. So you can just combine them and you get minus 1/2 thingy. Okay. There's also a thing here where this term zeroes out. I forget exactly. But so when you simplify this, whoops, 1239, you can get equation 1240. Okay. And I don't remember all the steps. So then the next thing we're going to do is we're going to say, remember we have 3 partial derivatives. The first one was for W. The next one, so this is, the next one is with respect to B, says this summation of A times Y equals, is the partial derivative. We're setting this equal to 0, so that's how that term went away. It's because this term is 0. And then this expression, C minus alpha minus gamma, that's also 0. And so that's how this term is going to go away, because this is just the sum of a bunch of zeros times C. And so in the end, we'll just be left with these two terms, the blue one here and this one here. And so now using Lagrange multipliers, we've turned this into minimize this expression here, subject to all of these, the sum of these YA products must be equal to 0. And if you do, if you do the derivation, you'll see that every single one of our alpha values must be between 0 and capital C inclusive. There's a bunch of math in the derivations. I don't think it's like super important if you just sort of, trust the math. But so now we have this alternate formulation, and this is the one that generally is used when you go to scikit-learn and you're using support vector machines. It's generally this formulation. And what you'll see here is we've got a bunch of y's. These are our labels, right? We've got a bunch of these alpha Lagrangian variables. And the only place where the data shows up is in this first example dotted with second example. So when we sum over all possible I and all possible j values, if there's capital N examples, we're going to have n squared of these inner products. And the inner product symmetric, so I inner j is equal to j inner I. Nevertheless, just in terms of the way this is written, there's going to be n squared of them. And we're trying to minimize this whole summation thing. And so if I just sort of started out by giving you a square table that showed you all the pairwise inner products between all the different samples, you could very, very quickly calculate what this double sum. Does that make sense? That if you just had all those inner products sitting around, it'd be very, very easy to just do a whatever 2 for loops and just calculate this. All right. There's another section here, 12.3.2, that says that if you look at this formulation, there is a geometric interpretation. I'll go through it quickly. I don't know how valuable this intuition is. But basically, they define the convex hull, which I find kind of intuitive geometrically, right? It's like the minimum polygon that encloses all the points. Okay. Mathematically, the way you can define it, though, is that like this line between these 2 points here is all the interpolations between this point and that point. And so this is basically some fraction between 0 and 1 of this point plus 1 minus that fraction of that point. Okay. And so all of the points on the perimeter are just going to be interpolated between 2 points. And it turns out that all the points on the interior you can also represent as a sum of the different points in here. Some of these you'll be able to represent, well, many of them you'll be able to represent multiple ways. Okay. Because in 2 dimensions you only need, right, you only need 2 things to span the space. But the whole idea is they're going to show that basically if you've got a bunch of coefficients and they sum to 1, and you multiply those coefficients by each of these points, then you can represent any point in this convex hull, including the actual blue dots, including the lines on the outside perimeter and all the interior points. And so this expression of some constant that sums to 1 times x, this is a thing that actually appears in our support vector equation. All right. And so basically what they're saying is, so then when we define our convex hull around the positive and the negative points, if we were to geometrically find the closest point between those 2 convex hulls, this is going to end up being twice our margin. And our hyperplane is going to go at the halfway point on this dotted line, and it's going to separate these convex hulls. So for me, it's not much of a leap to say, hey, separate all the individual points from saying exactly separate the convex hulls of those. So it seems pretty reasonable to me. Okay. So there's a bunch of math here that goes and shows all of this. Yeah, so I tried to talk through the intuition. I'm not going to go through all the math. I didn't find it super helpful. All right, so now we hopefully have a little bit of intuition. Um, we have defined this convenient dual form of the problem, and here it is, equation 12.41. This is our definition of the problem. And this is the one where, again, we have some different variables, but the data itself only appears in this one single inner product. And it turns out that in machine learning, there are multiple problems that have this same phenomenon, that the only place that the data shows up is when it is being inner product with other data elements. At no point is the data being inner product with one of your parameters that you're optimizing. So in other words, what they say in the book, I forget the exact wording they use, is but that the structure of all your parameters is completely independent of the structure of all of your data and your inner products. So remember how I told you if I just wrote a big square table that had all the inner product values, you could very quickly compute this, right? What if I just swapped those inner product values for a different set of inner product values? You wouldn't have to change your code at all. You would just have 2 for loops and you would calculate all this. So the question is there something I can do to change these inner products? And the answer is yes. Okay. So a simple thing I could do is I could double all the numbers, and then quickly you'll see the inner product is just going to be 4 times whatever it used to be. Okay. And you can still work this problem. But I could also do something else. I could square all of the x values, right? I could do any kind of transformation. I could do nonlinear transformations. I could do anything as long as I'm willing to do the work of calculating the inner products between the newly transformed values. So just like in polynomial regression, we started with our original data points. In polynomial regression, you say I'm going to have new features. I'm going to replace my x's with let's say I do a quadratic, right? So then I'm going to have something times x squared plus something times x plus a constant. So I'm going to have 3 times as many total features in my quadratic equation than I did in my original equation. I could do the same thing here, and then I could just take the dot product between all of these quadratic terms, right? And so if I did that, then basically I would be transforming my problem with my x's that are d-dimensional into a 3 times d-dimensional problem. I could also transform it into a 10 times d-dimensional problem. I could transform it into a d-squared dimensional problem. I could transform it into a billion-dimensional problem. Technically speaking, and they mention this in the book, you can even transform it into an infinite dimensional problem as long as the dot product doesn't explode, right? If it's sort of like a convergent series, then you can have an infinite dimensional space as long as you know what. So the only requirement for transforming these x variables is that I have to be able to give you a new table of all the pairwise dot products. The kernel trick, which the book does not go into detail, and I'm kind of thankful for that. But basically, the kernel trick is, what if there's a transformation of x's you can do that is cheaper to calculate the inner product of the new x's than it is to actually transform the x's and actually dot the transformed items. Okay, this is where I don't have the math skill to give you a really good intuition. But if it's not the case that the inner product is easy to calculate, just brute force it. Okay, transform each x into a quadratic or whatever, and then do the dot product and blah 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 blah. Bob's your uncle, you're done. But if we look over all the possible transformations of x under the sun, we can specifically look for the ones where when you transform X, like let's call it Xi and X sub J, and you dot them, because of the way we know the dot product works, a whole bunch of these terms are just going to cancel out. And that'll mean that the new dot product is actually faster to calculate without actually explicitly transforming Xi and X sub J. And so anytime that you have this property where the inner product is faster to calculate than brute force, that's what they say is an opportunity to apply the kernel trick, because we just need this square table of all the dot products. We don't actually need Xi and Xj never appear by themselves. Only the dot products appear. So as long as you can calculate the dot products, it does not matter what you actually did to the Xis and Xjs. And so here visually, you can see, and so this phi function is how we're transforming X. And I don't think it appears in the book, except it appears on like page 1 of the chapter, and then it magically reappears here in the last section. Okay. But so here's our SVM with a slightly different set of blue circles and orange X's. And this is the original problem. This is just linear. Okay. Now, let's go down here. So here they have a quadratic kernel, and what they've done is they transformed each x into a quadratic equation. So they have x squared, x and constant terms. Okay, and so they map this from a 2-dimensional space into a, I'm not sure, I think 6-dimensional space or something like that. And they built the SVM using inner products in the 6-dimensional space conceptually, okay? And they figured out what this solid line and these dotted lines are with the 5-dimensional hyperplane in 6-dimensional space. Then they did the inverse mapping back to our original x's and said, where does the 5-dimensional hyperplane show up and where do the margins show up? And what it looks like is these parabolas that you now see. So, so even though our original x's are like this, we're able to get a very different looking margin. And in fact, in our original 2-dimensional space, it's not even continuous. It's got like 2 separate components to it, right? In the lower right is a cubic, is a 3rd-degree polynomial, and they're able to do a bunch of stuff. And then one of the most common ones you'll see is this Gaussian radial basis function kernel, which the formal definition of it is this infinite series that converges. And so you're actually transforming each point into an infinite dimensional space, calculating the dot products. But again, if you know that this is the way you're going to do the math, and you dot them, and you're summing like whatever, xi sub 1 to xj sub 1, and then the 2's, and then the sub 3's, and the sub 4's, that's just a sum. That's going to form an infinite series. And as long as that infinite series of the dot product converges, you don't actually need to explicitly write out xi and xj. You can't write them out. They're infinite. But you know what they're going to sum to when you take the infinite product. So this is the example that kind of like hurt my head the most when I first saw this. But the idea is that you know the formula for the dot product. You can write the closed form formula for transformed xi dot transformed xj. And if you're really lucky and a bunch of the terms cancel or converge, then you never need to actually write out xi and xj. You just need to know what all the dot products are. And so the intuition around the radial basis function is just imagine that you form a little bit multivariate Gaussian, and so in this case it would be 2-dimensional Gaussian around each point. Okay, and those Gaussians extend infinitely far, but of course the probability gets very low the farther you get. All right, and so you're using that sort of as your distance, your similarity metric. So if you have a very small, tight Gaussian, any point that's very close to it will have a high similarity metric, but points that are very far away will have a very low similarity metric. Okay. And again, that's what I said at the very beginning is that for this inner product, we need some similarity function. It does not have to be the Euclidean one. It has to be any function that for some things they'll be defined as being highly similar, and for other things they'll be defined as non-similar. So in this radial basis function, any point that's super close will get a high similarity score, and any point that's far away will get a low similarity score. In the extreme, if you do not regularize this, what'll happen is you'll just get an island around every data point, and it'll be 100% overfit to your data. Okay, so it's extremely important when you use the radial basis function, you need to regularize this. And so what they show here, they don't show what the regularization C they used is. You can see we don't have, if there's what about 20 data points or so, we don't have 20 islands. We actually only have 3-ish islands, and that's a good thing. 3 islands might generalize. 20 islands would be extremely overfit. Okay. And so the formal math says that we're going to define a kernel K. And so X is our data space. And so this kernel is going to do an inner product between 2 X's and return a similarity score. Okay. And so basically, I don't know the definition, the definition of Hilbert space, but basically our function phi is going to transform each data point into a new space. In our case, there's no point in transforming to lower dimensional space. Okay, what we want is a higher dimensional space to make it easier to separate things. So we're going to transform it into higher dimensional space. This could be like R10, okay? And technically speaking, the Hilbert space, it could be R infinity. All right. And then we just need some feature maps so that when we take the dot product, the inner product between 2 data points, xi and xj, that we can figure out what the inner product would be in that space H. And we can brute force it by doing it manually, or for certain functions, there is a very convenient closed form, and you don't need to actually ever convert. So it's a little bit like I mean, this is not a very good analogy, but like if I said to you something like add the numbers 1 plus 2 plus 3 plus 4 plus 5, like if you're clever, you know there's a closed form formula for that. And so if I said add all the numbers up to 100, you could sit there and you could add all the numbers 1 to 100 and be like, it's n times n minus 1 divided by 2. And you could be like, here's the answer when everybody else is like plus 6, plus 7, plus 8. It's the same idea here. If you have a nice closed form formula for what the inner product is in the transform space, why bother just go and brute force everything when you have the closed form formula? Okay. So that's my best attempt to explain the kernel trick, even though I don't have the deepest mathematical understanding of it. And that's so one more where they just talk a little bit about the formula, but let me pause here because this is where I got lost the first 15 times I heard support vector machines. So comments, questions? It is, and it's just got a very formal definition of the trade-off between your definition of near and yeah, I guess it's really just basically that, right? So by changing the parameterization of the Gaussian, if you make it really tight, then the definition of near is very super strict. And then I guess instead of K nearest neighbors, it's more like neighbors within this radius or something like that, right? That's kind of the gist of it, right? And so when you define your margin, it's based on sort of that radius. That's my intuition. I hope that's mathematically accurate. But yeah, in a way, this is you. You could very loosely think of this as like a very formal way of improving k nearest neighbors to do classification. Yeah.
Hi there. I have a question.
Yeah, hold on
Uh,
a second. I hear you, but the audio in the room's not quite working. So, okay, try it again.
yeah, can you hear me?
Yes.
Hey, thanks for the wonderful explanation presentation, Ted. So one question that I had was, so the loss function here has like non-zero contribution from only the support vectors, right? The vectors that are defined as support vectors.
Yeah.
So but here in our minimization criteria, we're looking at all the pairwise products there. I mean, across all the points from 1 to n. I vaguely remember something about the alphas for non-support vectors being 0, but I'm kind of forgetting how that happens. Um, is there any intuitive explanation that you could provide
Yes.
about that? Yeah.
I'm trying to look at this formulation and uh, um, so in this nomenclature, I think the yi's and yj's are the plus ones and minus ones. Okay. And so
Mhm.
basically, we're going to have the, I don't remember if I've seen a different formulation where like the alphas have to sum to a particular value. That's kind of the way I think of it. Um, uh, but basically, yes, what's going to end up happening, uh, I may not get the math 100% right. Okay, so assume that your alphas for the positive class sum to a particular number. Okay, I'll just say one. All right, um, and you can apportion them any way that you want. Okay, then uh, when you when you have this similarity or distance between 2 points, you would want to apportion big alphas to points that are really close together. Okay. And you want to apportion as little as possible to points that are far apart. And ultimately, what happens is when you optimize this problem, if you have 2 points that are on the, like one positive point that's on the margin and one negative point that's right on the margin, what you're going to end up doing, oh, you get the door. What you're going to end up doing is you're going to end up putting all of your chips on the one point that's the closest to the other class, and all you're going to put 0 on all the other ones, because why would you put more weight on points that are farther away? So yes, I don't think in this book, I don't think they talked about it, but the intuition is that you're basically going to say, my alphas are all 0 everywhere except on these points that are the closest to the other class. And then for the negatives, you're going to do the same thing. You're going to set them all to 0 except for the points that are closest, and that will minimize this whole thing here. And then I never really terribly loved the name, but so they say that because everything else falls away because of the zeros, if you look at it, this minimum is going to be supported. This minimum is going to be built of nothing but the the data points X that are the ones that are the closest to the other class. And so they are and now again, in geometry, these data points, they're just vectors. They're just, you know, a bunch of numbers. And so support data points or support vectors define the margin. That's, they talk a little bit about, there's I think they call it the representer theorem in section 12.4. And they say that there's other problems that have sort of this similar formulation where basically this is ultimately just a combination of certain data points, right? Just there's a bunch of constants times these data points. And so uh, they said that if you what did the book say? It said if you look at a vector space that's defined by the data points, then ultimately only the points that are left over, these support points, are going to define a subspace of your total. And that subspace is, in fact, how the solution to this minimization gets defined. It lives in the subspace of just those points. Obviously, it lives in the full space as well, but the kind of cool thing is that, let's say you had only one positive and one negative point that were on the margin, then basically, if you just look at the line between those 2 points or whatever, or the plane defined by those 2 points or whatever, like that your solution essentially is going to live within that tiny subset of the full space of all of your data points. I don't know if that answered your question.
Yeah, it did. I think it made a lot of sense. Thank you so much.
Yeah, thanks for the question.
Yeah, it's very intuitive.
Any other comments, questions? Yeah. So if you solve this problem, then basically you can say, just tell me the alphas that are non-zero, and that's going to be your data points that are your support vectors. So minimally, you might only have one positive class and one negative class. And again, we define this with these slack variables. So the definition of support gets a little bit weirder because you can have things that are on the wrong side of the margin at some level of penalty. And that's where your C decides how much do you care about that versus how much do you care about your margin being pretty versus how much do you care about every single point should try to be on the correct side of the line. And so, yes, so with like the radial basis function, what I was talking about being overfit, you can force it to have no points on the wrong side of the line, but it just won't generalize because you're just going to have an island around every point. It's kind of pointless. That's k nearest neighbors k equals 1 or something like that, approximately,
And I want to show 2 visualizations related to those, if I can share screen for that.
Yeah, awesome. Go for it.
So when I think of SVMs, I have 2 images that are burned into my head. So there's the ones that were shown in the book are good, but I have these like base cases where it's like this is what I think of when I think of SVM. So this is, I don't know the deep math behind these concepts. There's this whole VC dimension stuff, but I think of these 2 plots. So I'll show the second one later. But basically, just imagine you have these 3 points and you want to separate them. You can draw a straight line through them to get any combination of pluses and minuses. It doesn't matter which is plus, which is minus, what their arrangement is. But once you get to 4 points, if you align them correctly, you cannot separate them with a single line. You need a second line, or you need to apply a kernel trick or something. So like that's to me, that's like the simplest base case. Like the other diagrams were a little bit more complicated, showing here's the different spaces. But this is like the problem that we're solving for. It's like you cannot draw a straight line through those 4 points and get them on the correct side of all of those cases.
That's cool.
I can link this, but it's Bapnik Berlinski dimension, VC dimension.
Bapnik's one of the SVM guys.
And then the other one is this one, which is showing a similar concept, but it's just a very simple transformation showing, look, before we had this X1 dimension, you can't draw a line through both of the negatives and the positives. But if you just say X1 and X squared, then you can get a straight line through this piece, and it's simple now.
Yeah.
And so that's the whole core of the SVM. So.
The original problem on the left is 1D. The problem on the right is now 2D. We've increased the dimensionality, and we took something that was not linearly separable, and now in 2 dimensions, you can see the dotted red line. It is linearly separable, whereas it wasn't. Yes, this one is burned in my brain. I had mentioned it to Anastasia, but she was sick and didn't have a chance to add that to the slides. But I'm glad you pulled that up, because that was immediately what I said to her. I was like, that X squared thing is not in the book. Awesome. Any other questions or comments?
This is still large amounts of data. We took kernel tricks to avoid all the products. If there's no kernel trick, you need to force them. So lots of data could be a problem, right?
Yeah. So if you look at scikit-learn, basically what they're going to say is, here's a list of 12 different functions you can use that all have really convenient shortcuts that the kernel trick does work. And so we support all of these. If you want to do something else, your SOL, what you can do is you can manually explicitly transform all of your data. So just like there with Ryan's example, they just showed manually creating an X squared extra feature, and that made it separable. Okay. So you can manually create extra columns in your data and hope that that helps. But if you use one of the kernels that's available in scikit-learn, then you don't have to do it. You just tell it use this kernel, and it'll automatically figure it out for you.
I can list this help with like the game descent or
Yeah, I believe it is using gradient descent. So we have one more section which doesn't go into a whole lot of detail, but since you asked, why is my thing not minimizing? Go away. So they say numerical solutions, all right, and there's the primal form and the dual form. If you write out the equations and you do it in matrix notation instead of with summation symbols and stuff, eventually you can write it as this equation, minimize these matrix vector type products and sums subject to this rule, and then the dual can be written as, and this is the one that usually gets used, minimize this gigantic product here, subject to this rule. And then my understanding is, yeah, you run gradient descent, but this is a convex quadratic. Wait, I think I wrote it here. Both the primal and the dual are convex quadratic programming problems. And so those are known to have only one minimum. So the local minimum will be the global minimum. And in that case, you don't have to use regular gradient descent. You can actually use a second order optimizer like Newton's method, or what is it called? LGBFS, LBG, I don't know. But anyway, you can use any optimizer you want. Gradient descent will be slower than a second order one. If you use second order, it'll converge in a very small number of steps. Each step will be more expensive because you need second derivatives, but it'll converge much faster. And I think there's also methods that are like approximate second derivatives instead of exact second derivatives. But yes, you can use any optimization technique, and it's guaranteed to converge and reasonably fast, and it will be the global minimum. It'll be the exact solution, barring floating point rounding and that kind of junk. So the book never really goes any further than this. And I was kind of cool with that. I was like, okay, like there is a level of understanding I could have that's a little bit deeper if I actually spent more time looking at these equations. But at the end of the day, it's like, yeah, it's a quadratic equation. It has one minimum. I would not be able to code something to solve this just looking at this slide, but I'm very clear that there are many people who can code that very quickly for just a quadratic problem. Convex quadratic problem. They also mentioned something about in this formulation, all the alphas are between 0 and C. And so basically this is a multi-dimensional box or cube where each one is between 0 and C. It's not a funny shaped thing. It's actually a rectangular or square box. And so they said that you can actually solve it really fast because I believe there's for this kind of problem, your solutions are always going to lie at either a vertex, a corner, or along an edge, but never the interior of the box. And so there's this like really fast solver. I think, Ryan, you mentioned the other week where you start at a certain vertex and you just walk the edges until eventually you get to the exact solution. But there's a combinatorially fairly small number of edges to walk compared to the entire continuous interior of the box. So yeah, so there's a number of different ways I think you could solve it, and maybe it turns out that walking the vertices is faster than gradient descent. Yeah. Yeah, sure. Yeah, so inference, that's a great question. They didn't talk about this at all. So once you've actually solved for this, you now have your W and your B. Okay. And so basically what you do is for a new data point, you get all the values for my new data point X, and you just take W times X plus B. And is it greater than 1, greater than 0, or less than 0? And voila, you have your class. Okay. Now, in the case where you used a kernel, okay, technically now you're not doing X, you have to do phi of X, the transformed version of X, okay? Which is a little bit trickier if, say, the transformed version of X is an infinite dimensional space, okay? But nevertheless, there are, you know, if it's just like quadratic or cubic, that's not a really big deal. You just convert X, whatever. I don't remember exactly how you do it for radial basis function, but again, the same thing that allows the inner products to converge, you can basically figure out whether W times that transformed data point plus B will be positive or negative. And you don't need the exact value, you just need a sign. So, you know. Yeah. Yeah. And in fact, I mean, we could bring up the scikit-learn page. There's my I don't know if it says anything about I don't know, there's a whole bunch of stuff here. Sorry, I couldn't hear you.
Talks about probability.
Yeah, the book mentions there are some tricks to try to get to try to get something more than just a class prediction. Theoretically, you can just sort of say like how far away am I from the hyperplane, but I don't think there's any definition of scale. So if you do one inference, and it says 5. You're like, well, is 5 big or is 5 small? I don't really know. But I don't think it's that hard to try and figure out, based on what your training set is, you can figure out is 5 actually like pretty big or pretty small or something like that. It doesn't seem intuitively like it'd be that hard, but it's not giving you something that is easily interpretable as a probability. So, I also mentioned the book mentioned that when you do classification, there's typically 3 values that you might have that you're working with in your model. You might have a raw score. So if we're using sigmoid or softmax, then you might refer to that as a logit, okay, or whatever, okay. But you have a raw score, which is typically real numbers, okay. You have something that you interpret as a probability type score, a number between 0 and 1, okay. And then after you choose your threshold, the default might be 0.5. After you threshold it, then you'll just have class A or class B. I bring this up because when calculating metrics, for some metrics, you need class A or class B or whatever your classes are in order to calculate the metric. So for example, if you were just going to do like accuracy, okay, you need the class. But if you're doing other things like you want to do the rock curve and you want to know the area under the rock curve, you cannot give it classes. You have to give it the probability scores, or you have to give it a score because it has to sequence them. And I say this because I've actually had this come up at work where somebody like gave me this. I'm like, this rock curve doesn't look right. It's like a step function or whatever, and it's because somebody passed in the classes instead of passing in the raw scores. So I thought that was a good note that it's not that you only need one or the other. That would make life easier. Depending on what your metric is, sometimes you need the one and sometimes you need the other. And so it's good to keep track of that you don't accidentally pass in. So when you say like y hat, well, what is y hat? Is y hat 1, 0? Or is y hat a number between 0 and 1? Or is y hat a number between negative infinity and positive infinity? And you kind of need to know in order to do the right metrics. All right, cool. I think we'll stop here then.